At the end of the last recording, I was discussing the mathematical expression for the force between two electrically charged objects. I had gotten the expression that you can just barely see here. So the magnitude of the force is equal to some proportionality constant times the product of the charges that each of the two objects carry, divided by the square of how far apart the two charges are from each other. And I said at the end of things that, so that's the magnitude. Now we also have to worry about the direction. So let me do that. Well, in the drawing that I made here, the force on Q1 due to Q2, well, like all forces, it has to point from the source of the force to the object that is feeling the force. The way the question was asked, what is the force on Q1 due to Q2? In that case, that suggests that the force has to be parallel to this line here that I've labeled R as the distance between the two objects. There's one more piece of property of electric charge that I mentioned but didn't make absolutely definitive, so let me do that now. I was talking about earlier properties of charges, and I mentioned in the previous recording that there's two types of charge. And I said that they cancel in the sense that the forces they create cancel. I also mentioned about conservation of charge and quantization of charge. But I want to focus your attention on this whole thing about the charges cancel. Again, what I mean by that is that a positive charge will exert a force, a negative charge can exert a force or create a force, and the forces that they create, the forces they exert, point in opposite directions. Another way of saying exactly the same thing, let's see, put it over here, is charges, objects that carry the same sign of charge, the same kind of charge. They're both positive or they're both negative. So-called like charges. So let me actually just say same sign charges, charged objects repel each other. They exert forces that push them away from each other. Whereas objects that carry charges of opposite sign, one positive, the other one negative, attract each other. So whatever these objects are here in my diagram that I have labeled Q1 and Q2, since they carry opposite sign of charges, sorry, I've got some tangled wires here that I have to deal with. Since Q1, object Q1 and object Q2 carry charges of opposite signs, then they're going to attract each other, which means then that when I draw my force arrow on here, my force arrow is going to point that away, and actually I'll leave it like this. So I'll use that light brown there for the distance between them, and then I will draw a force vector here, and that's my electric force vector. Okay. So now, then, again, that means in this expression here, I need to attach a direction to this, right? And the choice that I'm going to make is going to be determined by what coordinate system I choose. All right, and so we need to choose a coordinate system, and I'll do that. And let's see, what color do I want to use here? I guess I can use brown. So let's put a coordinate system on this thing. So step number one. In fact, let me just formalize this. The question is, what force does Q2 exert on Q1? All right, so step one to solve any physics problem is to draw a diagram. Okay, we've done that. I drew my objects. I labeled them Q1 and Q2. Why Q, by the way? We universally use the letter Q, sometimes capital Q, sometimes lowercase q. A lot of times we'll mix them up in the same equation. We use letter Q to represent electric charge. Why Q? Because we weren't using letter Q for anything else. We don't want to use we don't want to use the letter C because we're already using C for the SI unit of electric charge, the Coulomb. I don't want to use lowercase c because it turns out lowercase c represents the speed of light, so that's pretty important. So we couldn't think of anything else, but Q wasn't doing much of anything, so Q it is. All right. So when you see Q, that is universally the symbol for electric charge. Okay, so there's our diagram. We've got our charged objects. I've labeled the distance between them, and then I've drawn the force on the so-called test charge. I'll formalize that language in a minute. Q2 is the source of the force. Q1 is the thing feeling the force, or experiencing the force. The language that we use in this context is that Q2 is the source charge, Q1 is the test charge, and I will discuss that in more detail in a while. So there's our diagram. Step two in solving any physics problem is impose a coordinate system. Okay. The reason we need a coordinate system, well, there's lots of reasons we need a coordinate system, but in this case, because I need to be able to indicate the direction of my force vector. And so we'll choose a coordinate system, and there's a lot of perfectly fine choices. I think I will do this one. I'll let this be the x-axis, and I'll let this be the y-axis, and we'll put the source charge at the origin, or more correctly, we'll put the origin at the location of the source charge. That's perfectly arbitrary. I could have done it. I could have put the origin where my test charge is. It hardly matters. But I had to do something. Okay. So there's our coordinate system, and now it's 3, solve the problem. Well, mostly what I've done here is just set things up so that I can finish writing my force function here. In this particular example, in this diagram at least, my force is pointing downward in the negative y direction. Okay, so I could label this, if I wanted to, I could say that my force then is in the negative y hat direction. And I've not been given any numbers, so this is all I could do. And this would be perfectly fine, and this is correct, and this is the answer to the question. So far as I have been, since I wasn't given any numbers, this is all I can really write. But I want to sort of expand on this theme a little bit. Specifically, what about this direction? Okay, so there's my example. Yay, okay, it was done. Let me redraw this, and I want to show you something. So let me construct this situation one charge at a time. So I'll put my Q1 here. And I put my Q2 here. Negative. And as I just did, that would indicate that actually, let me do something. Let me make my life a little simpler. Let's make them both positive. Why not? Make them both positive. So this is Q1 and this is Q2. Okay? In which case, according to the rule that I just mentioned to you a moment ago, these two charges, hi. Hold on 1 second, let me pause the recording. Security just stopped in. It's 8 o'clock at night on a Saturday night, and here I am recording this lecture. I'm lecturing to an empty room. So this is very exciting for me. Okay. Where was I? All right, so so Q1 is my source charge, Q2 is my test charge. Q1 is the source of the force, Q2 is the thing experiencing the force. The direction of the force on Q2, due to Q1, in this case, according to the, sorry about that, my microphone, according to the rule that I mentioned here a moment ago, like charges repel each other, same sign charges repel each other, opposite sign charges attract. So here, in this drawing, they have the same sign, so Q2 is going to be repelled by Q1, and so the force vector that I should draw will point like this. Okay? That would be the positive y direction if I used the coordinate system that I did before, but I'm not going to. Because what if instead I put a positive, I move my charge over here? I'm not going to erase that force for reasons that you'll see in a moment. Well, I don't think you'll struggle to realize that the force on Q2 now is going to point this way. If I put it instead here, I'm doing my best to maintain the same relative distances here. The force on it would point this way. And over here, if I put it over here instead, it would point this way. Force. Okay. And in fact, if I put my Q2 anywhere on this imaginary perfect circle, see how that's a perfect circle there? Then if I put that anywhere on this perfect black circle, anywhere in that perfect black circle, that the force vector, assuming it's Q2 is a positive charge, is going to point everywhere directly away from the source charge. Okay? These are all forces. And that's the force that we would have if I put my test charge Q2 anywhere here. Okay? And notice that all of these forces, now it's no longer easy to say, oh, well, the force vector is pointing in the x direction or the y direction or even the z direction, because, by the way, please notice that if I put a positive charge out here in front of the board, that the force on it would point, wrong color, oh, yeah, would point out of the board like this, okay? And, in fact, if I put a positive Q2 behind the whiteboard, it would point, its force vector would point that away from the screen, away out into the whiteboard, okay? So in other words, this is a three-dimensional construct. I could have force vectors point like this, out here like this. In short, far from x, y, or z, I've got force vectors pointing outward in a spherically symmetric sense, and I've got an imaginary sphere here, and the force vectors are all pointing parallel to the radius of that sphere. And so the language that we use is we say that these forces are all pointing in the so-called radial direction. And we symbolize that fact with a unit vector, and the unit vector, we won't use x hat, y hat, or z hat because our force isn't going to be pointing just in the x direction or the y or the z directions. Rather, since it's going to point in the radial direction, the letter that we'll use for our unit vector is, reasonably enough, r hat. And then that completes the expression that I wanted. And this result here is the force between two charged objects. Now there's a restriction here that I'll mention in just a moment. But in any case, this relationship was first developed and derived by the same person who got the SI unit of charge named after him, Coulomb. And in fact, it is called Coulomb's law. Okay, a couple of things. First of all, if you've never heard of a unit vector in your life, either talk to me during class, or if I have time, I'll make another separate recording discussing unit vectors. But the short version here, all this is a symbol indicating that I've got a vector here, and the letter that you choose with this little hat thing on it is an indication of what direction your force is pointing. So if my force happened to be pointing in the x direction, I would use x hat over here. If it pointed in the negative y direction, as it did in my previous example, then I would put a negative sign on it, call it y hat. Z direction, z hat. In the radial direction, I call it r hat. It's just a letter indicating that you have a vector and what direction that vector happens to point. So this thing says this force here is a vector, which of course we know it is. And what direction does this vector point? It points in the r hat direction. R standing for radial. Okay, so that's all that's all a unit vector really means. Again, talk to me during class, or perhaps they'll be recording. The second thing I want to mention about Coulomb's law, as I've expressed it here, is that although it is true in principle for any two charged objects, as a practical matter, this is more of theoretical interest than of actual practical use, because, as I suggested in one of the early recordings, is that we almost never, unless you're a particle physicist, almost never have any interest in calculating the force between just two objects, two protons or two electrons, an electron and a proton, or whatever, some combination of very, very small amounts of individual charged particles. Almost all the time, the forces that we want to calculate are between large objects with vast, vast, vast numbers of charges in them. And so what I'm going to do in the next recording is do you a couple of examples of how we apply Coulomb's law for a couple of charged particles. Okay, but it's more, the purpose of those examples is highly artificial. It's just to get you comfortable with the idea of what Coulomb's law is. And then once that's accomplished, once you're sort of comfortable with calculating with Coulomb's law, then we'll take it to the next step and do more complicated charge distributions. And so there's that. One last comment before I end this recording, and that is something new has crept in here. I've been ignoring it for the purposes of thinking about other things, but I want you to realize it now, and that is that this force is different in one very important way from all the other forces that you've ever learned about. Okay, and back in mechanics, you learned about tension, and you learned about gravity, and you learned about spring force, and you learned about friction and various other forces. And with one exception, and the exception is the spring force, this is the first force and the first time that you've ever encountered a force whose magnitude depends on distance. If you think about it, gravity never depended on distance, tension didn't depend on distance, friction doesn't depend on distance. This is new. And the fact is that F the magnitude of this electric force, depending on how far apart your two charged objects is, that makes F incredibly difficult unless we're clever. And we're going to have a lot of recordings. We're going to have several recordings devoted entirely to dealing with F in a very clever way. And that'll be in the future. So next recording, I'll do you a couple of examples just to enable you to wrap your head around what Coulomb's law is, what it means, how you work with it.